Hello and welcome. We are going to be discussing alkalinity and hardness in this lecture. Some of the key learning objectives are to understand the carbonate system, the carbon dioxide, bicarbonate, and carbonic acid equilibrium, to be able to calculate and understand alkalinity for a given water sample, and then calculate hardness, total hardness, carbonate hardness, and non-carbonate hardness, and establish the relationship of alkalinity with hardness. Okay, first the carbonate system. Carbonate system starts with the dissolution of atmospheric carbon dioxide to aqueous carbon dioxide. And when the carbon dioxide reacts with water, it forms carbonic acid. And this carbonic acid is a weak acid, so it dissociates to form H plus and HCO3 minus, that is bicarbonate, and the pKa for that reaction is 6.4, and bicarbonate further dissociates to form another H plus and a carbonate ion, and the pKa for that is 10.3, so which indicates, these values indicate that these are weak acids. So what happens when this system, if you imagine these different ions, the carbonate, bicarbonate, and carbonic acid in a closed system, that means the total carbonate is same. They can just transform from one form to another. So if you look at this plot, the x-axis is pH and y-axis is the percentage of one of these species in the total dissolved carbonate system. So it's interesting to note how these different components predominate at different pH ranges. When pH, so there are three critical points, when pH is below 4.5, all the carbonate is present as carbonic acid. In between 4.5 and 8.3, there is a mix of carbonic acid and bicarbonate. At about 8.3, all the carbonate is present as bicarbonate. And from 8.3 to 12.3, there is a combination of HCO3 minus and CO3-2 minus. But after 12.3, all the carbonate is present as CO3-2 minus. So this shaded area shows the pH range in nature. So in nature, that means the predominant species would be bicarbonate and sometimes carbonic acid, but for most part it's the bicarbonate which is a predominantly occurring species in nature for the carbonate system. If however the pH increases and goes above 8.3, goes towards 9, 10 or 12, then the carbonate ion also starts coming into play. Alkalinity is defined as the buffering capacity of any given water, or the ability to neutralize acids and bases to maintain a fairly stable pH. It's also defined like if you can experimentally determine alkalinity of a water sample by adding acid, for example sulfuric acid, and do it to keep doing it to bring the water sample to a pH of about 4.5. If the water has high alkalinity, it will take more acid to bring the pH to 4.5. If the water has low alkalinity, it will take less acid to bring the pH to 4.5. Mathematically speaking, alkalinity is a sum of the bicarbonate, carbonate, hydroxide, and H plus ions. And this is the formula in moles per liter. Notice that the carbonate ion has a multiplier of 2 in front of it. If you ignore hydroxide and H plus, then that's called approximate alkalinity, which is a pretty big percentage of the total alkalinity. And so sometimes people just use these two ions. And in natural systems, as we just saw, carbonate may not even be present many times, so it might just be the bicarbonate ion. The source of alkalinity is rocks and soils, salts, certain plant and industrial activities, calcium carbonate, limestones. Now, a lot of times alkalinity is defined as in the units of milligrams CaCO₃ per liter. So for that, we would take all the species, like these 4 species, bicarbonate, carbonate, hydroxide, and H+, and then with each of them we will use this formula where milligram per liter as species or ions, and then multiply by the equivalent weight of calcium carbonate divided by the equivalent weight of the respective species. And equivalent weight is the molecular weight divided by the valency factor. The valency factor is, for most part, especially for this course, for most part, it would be the charge on the ion. So for aluminum, for example, Al3+, the atomic weight is 27, equivalent weight is 9, which is 27 divided by 3. For calcium, the atomic weight is 40, the equivalent weight is 20, which is 40 divided by 2, the charge on calcium. For hydrogen, both the atomic weight and equivalent weight are 1. For magnesium, the atomic weight is 24 and the equivalent weight is 12. And for sodium, because it's singly charged, the atomic weight and equivalent weight are same. And so forth. I think you get the idea of how do we calculate the equivalent weight. Typical alkalinity ranges for rainwater, because it's not yet come in contact with any soils or rocks, it's pretty low in alkalinity. It's less than 10 usually. Surface waters at 20 to 200, and surface waters where there's more alkaline soils would be a higher value, up to 500. Groundwater, because they are more in contact with some of these carbonate minerals, they have much higher alkalinity values. And then seawater also has relatively high alkalinity value. Now, what might be the difference between alkaline water and water with high alkalinity? There is some people think they're both same, but that's not true. Alkaline water is water which has a pH more than 7, and then water with high alkalinity is one which has higher buffering capacity to resist the change in pH. So they sound similar, but they are vastly different. Let's take up an example now. We'll switch to the notepad and we will solve this example together. I encourage you to solve along with me and with your pen, papers, and calculators. It's a helpful exercise to try to solve these problems.
Okay, let's consider this example to calculate the alkalinity. Here we are given carbonate and bicarbonate concentration and pH equal to 10. So first let us write down the definition or the formula for alkalinity. So also notice that we need to calculate in both millimole per liter and milligram per liter CaCO₃. The formula for the two is slightly different. So for this, so this is the formula where all these species are in the units of millimoles per liter. And for milligram per liter CaCO3, it would be in this case all are in the units of so we will use both these formula for solving this problem. Okay, so what are we given? (100 milligram per liter of carbonate, 75 milligram per liter of bicarbonate, and pH is equal to 10, which implies that H plus is 10 to the power minus 10 molar and that OH minus is 10 to the power minus 4 molar. Okay, and how do we get that? Because we know that H plus times OH minus is equal to Kw, which is the equilibrium constant for dissociation of water, which is equal to 10 to the power minus 14. So that's where we're getting this from. Okay, so what I'd like to do next is make a big table. So I'll make a big table here and I will write all my species of relevance. Okay, and next I will write their different concentration units. This is milligram per liter as ion. And then let's also write down their molecular weight, their N, which is the valency factor, and then okay, so for CO3 minus, it's given this is 100 milligram per liter. This is 75 milligrams per liter. OH minus is not given directly. Let's also write down in millimoles per liter here. And molecular weight for CO3 minus. So this is, let's see, carbon is 12, oxygen is 16, hydrogen is 1, so CO3 minus the molecular weight for CO3 minus would be 12 plus 3 times 16, which would be 60. For HCO3 minus, it would be 1 plus 12 plus 3 times 16 would be 61. And OH minus would be 16 plus 1 equal to 17 gram per mole. So we can just write these down. This is 60, 61, 17, 1. The N is 2, 1, 1. That's the charge on the ions. So milligram per liter CaCO₃. So just recall. Now how do we calculate? So we calculate that as and equivalent weight of CaCO₃ is 50 gram per equivalence. So this would be 100 times 50 over 60, 75 times, okay, sorry, this should be 30 because the equivalent weight would be 60 over 2. And this would be, okay, OH minus we said is 10 to the power minus 4 molar. So this would be 10 to the power minus 4 moles, and 17 into 10 to the power 3 milligram per liter. And H plus would be 10 to the power minus 10 to 1 into 10 to the power 3. So this would be and this would be 10 to the power minus 7. And let's first calculate these numbers. So this would be 167. This here would be 61. I'm rounding it off. This would be 5. And this could be, we can approximate this as 0. And now if we do millimoles per liter, so this would be 100 milligrams per liter divided by 60 milligram per millimole. This would be 75 divided by 61. This would be 1.7 or 17 into 10 to the power minus 1 divided by 17, and this would be 10 to the power minus 7 divided by 1, and this would be equal to 100 divided by 60. If you plug that in the calculator, that would be 1.67, and if you plug this one in, this would be 1.23. This is 0.1, and this is, we can say this is almost 0. It's a very small value. Okay, So now that we have these, now we should be able to plug these back into the formula above. And okay, let's create some more space here. Okay, so as CaCO3, it would be 167 plus 61 plus 5 minus 0. So this is the exact alkalinity, and if I plug this in, this would be 233. And if we are doing approximate, so this is exact, and if we just exclude hydroxide, then that would be 228. So that would be approximate. And then if we do alkalinity in millimole per liter, that would be 2 times 1.67 plus 1.23 plus 0.1. So if you plug that into the calculator, that's 4.67. This is exact. And then if we exclude hydroxide, this would be approximate. So I hope this is clear to you. I urge you to go over this slowly and see if you have any questions, then please let me know.
Okay, let's look at hardness. Hardness is defined as the sum of all divalent cations, mainly contributed by calcium and magnesium, and the units are milliequivalents per liter or milligram per liter calcium carbonate. So total hardness would be a sum of calcium hardness and magnesium hardness. It's important to note that hardness is not a health hazard. It is unregulated in drinking water standards for that reason, but it still needs to be measured. And calculating hardness in milligram per liter as calcium carbonate, we take the milligram per liter of calcium as ion, multiply that by equivalent weight of calcium carbonate divided by the equivalent weight of calcium, which is 50 divided by 20, and do the same thing with magnesium, and then add the two to get the total hardness number in the units of milligram per liter as calcium carbonate. So what are the signs of hard water? Hard water is bitter in taste, and it forms a white milky film on the shower door or your bathroom tub or any of the shower area, any tiles. And what is this material? This is actually calcium carbonate that precipitates on the surfaces, any surfaces it can find. Also, hard water doesn't form soap froth in the soap, it forms soap scum because calcium from the hard water reacts with soap to form this soap scum, which hinders the froth formation. And then kitchen utensils and boilers and different kind of so all kinds of systems, you have this scales that form due to precipitation of calcium carbonate um, on those surfaces. And kind of an anecdote from my life, growing up early in childhood, I was residing in an area which had very hard water, and drinking that hard water, I became accustomed to the taste so much that soft water used to taste bitter. And so that's human conditioning. If you're exposed to hard water for a long time, that you become used to that. And then the source of hardness is also rocks and minerals and soils. And for that reason, groundwater is usually harder than surface water because it has more contact time with calcium and magnesium bearing minerals. What is the classification or the different ranges for hard water? 0 to 50 is considered extremely soft, up to 100 is considered very soft, up to 150 is acceptable, and up 150 upwards is considered hard, or and up to 300 up and above it's very hard. A lot of times when people are trying to soften their water, they tend to over soften it, but you don't need to go very low actually to get soft water. This is the map of the US showing the different uh, hardness ranges. You can see these different color codes. And this is the units of milligram per liter as calcium carbonate. East Coast and West Coast, you can see, are have more soft water than some of the interior regions in the states. And that's again, this map is showing clearly how it's all impacted by underlying rocks and geological formations. Now let's talk about carbonate and non-carbonate hardness. The total hardness can be defined as, we talked about magnesium and calcium, but then also we can define it as carbonate hardness and non-carbonate hardness. Carbonate hardness is one which is associated with HCO3 minus and CO3 minus. That's carbonate and bicarbonate. It's called temporary hardness. On the other hand, the non-carbonate hardness is hardness which is associated with other anions like chloride, sulfate, and so forth. And this is referred to as permanent hardness. Now, why is carbonate hardness temporary? Because um, calcium can react with the carbonate minerals to form a calcium carbonate precipitate and more easily get removed from the system. On the other hand, the non-carbonate hardness is difficult to remove from the system, and that's why it's called a permanent hardness. Alkalinity and hardness, they are, as we discussed, they both arise from when the water comes in contact with soils and rocks. And so here the schematic here shows that precipitation, water enters the soil via precipitation, and then it percolates and goes through the subsoil, the topsoil, the subsoil, and then the rocks beneath that, and then comes in contact with these minerals to um, gain alkalinity and hardness. If there's limestone, it's a source of both alkalinity and hardness, because limestone is calcium carbonate. It has calcium, which causes hardness. It has carbonate, which causes alkalinity. On the other hand, if you have trona, which is sodium carbonate, this doesn't cause hardness because hardness is caused by divalent cations, not monovalent cations like sodium. So this yields a soft but still high alkalinity water. And if you have gypsum, which is calcium sulfate, then you would get hard water because of calcium, but then it would be low alkalinity water. There is a hardness bar chart as a way to represent hardness, where you present all the concentrations in milligram per liter of calcium carbonate. These are horizontal bars. The upper bar you present all the cations, and the lower bar you present all the anions. So you can see here you make all the calculations in milligram per liter of calcium carbonate, and then use stack up horizontally all the cations and then stack up all the anions separately. And usually because the any water is neutral, so the cations and anions should be equal. But sometimes there's a slight difference because we are not able to measure all the different components in the water. So that doesn't mean that water is charged or it's not neutral. It just means that we did not include some of the minor ions in the measurements. And then this chart is very helpful to look at the relationship between the total hardness, the carbonate hardness, the non-carbonate hardness. Here you can see the carbonate hardness is um, coming from the bicarbonate, which is also the alkalinity of the system. So mathematically speaking, carbonate hardness is defined as the minimum of the total hardness and the alkalinity. So two cases arise. First case, when alkalinity is less than total hardness, and in this case, the alkalinity would be carbonate hardness, and there will be a non-carbonate hardness component as well. On the other hand, if alkalinity is greater than total hardness, then all the hardness is equal to carbonate hardness. Something to note here in these plots is that you usually would place bicarbonate as the cations calcium and magnesium would preferentially attach to or be associated with the bicarbonate, and if the bicarbonates are not present, then they go to others like chloride and sulfate, like in this case here as well. Let's now do a couple of examples. We will switch to the notepad and then solve a couple of examples together.
Okay, for this problem, we have to construct a bar chart for all the constituents given in this table, and for that we need to convert everything first to milligram per liter CaCO3. So as in the previous example, I like to make a table, and let's write everything down that's given to us. 103 milligram per liter of calcium, 5.5 milligram per liter of magnesium, sodium, bicarbonate, sulfate, and chloride. Now if we write the equivalent weights of these, for calcium the equivalent weight is 40 divided by 2 is 20 gram per equivalent. For magnesium it's 24 by 2. For sodium it is just 23 over 1. And for bicarbonate it would be 61 divided by 1. Sulfate, I would let you calculate the molecular weight, but if you do that, sulfur is 32, oxygen is 16, so 16 times 4 is 64, plus 32 gives you 96 by 2, that would be 48. And let's see, this would be, chloride would be 35.5 divided by 1. And now we can, using our formula, we can calculate this. 103 times 50 divided by 20, 5.5 into 50 divided by 12, 16 times 50 divided by 23, 61 sorry, 255 times 50 divided by 61, 49 times 50 divided by 48, 37 times 50 divided by 35.5. So if we put that all in the calculator, we will get, let me just put those in the calculator, and I get 257.5, 22.9, 34.8, and this is 209, 51, and 52. Now notice that there's a nice little division here. These are positively charged cations and these are negatively charged anions. So their total should ideally be, any water sample is neutral, so their total should be same. So this one is totaling up to be 315 milligram per liter CaCO₃, and this is pretty close, 312 milligram per liter calcium carbonate. So with that information, we can proceed to make our chart. Making some space in the sheet. Some more space. Okay, so our chart should look like this. This is what we have seen in the slides. Oops. So, and this is not exactly to the scale, it's a bit approximate, but you'll get the idea. So on the top I'll have all the cations. So the first one is calcium, and the calcium you will see is 200 and starts from 0 and goes up to 257, and I'm just rounding off the numbers here. And then after that it's magnesium, and the magnesium goes to 23, and so adding 257 to 23 gives me 280. And then sodium is slightly more than magnesium actually, so I can make it slightly bigger than magnesium. Let's modify it a little bit, and the total is 315. Now these are all the cations, and now I'll draw the bar chart for the anions. So anions would be in the bottom. The biggest chunk is the bicarbonate, which is 209, so slightly lower value than the calcium. So this is 209, and then we have the sulfate and chloride are almost equal, so I can just 209 plus 51 will be 260. So that's we have drawn the bar chart, and now we can look at this chart and do some other, get some other information from here. So calcium and magnesium we know is, so in this case this would be total hardness right here, which is 280, and then the alkalinity is contributed by the bicarbonate. So the hardness associated with bicarbonate, this would be carbonate hardness right here, and the rest would be the non-carbonate hardness. So we would have total hardness would be 280 milligram per liter CaCO3. The carbonate hardness would be 209 milligram per liter of calcium carbonate, and the non-carbonate hardness would be 71 milligram per liter CaCO3. So that's how we can use the chart and get a visual estimate of the water chemistry of the different constituents in our water sample. Okay, let's consider this example now. Water has an alkalinity of 200 milligram as calcium carbonate. The calcium concentration is 160 milligram per liter, and magnesium concentration is 40 milligrams per liter. The pH is 8.1. Find the total carbonate and non-carbonate hardness. So in this case, you recall when the pH is about 8.1, all the carbonate exists as bicarbonate. So the alkalinity that we have is equivalent to the bicarbonate concentration. So I know that the HCO3, let's see, okay, let's do it slightly differently here. This is 200 milligram per liter CaCO3 as ion and as ion. Okay, and now let's calculate the total hardness as CaCO3. So total hardness this would be 160 milligram per liter times 50 over 20 plus 40 milligram per liter times 50 over 12. And if we solve this, we get 400 plus 167, that gives us 567 milligram per liter as CaCO3. So that's total hardness is then 567 milligram per liter of CaCO3, and carbonate hardness, if you recall, is the smaller of, it's a smaller value of the total hardness and alkalinity. So in this case, total hardness is 567 and alkalinity is 200. So this would be, the carbonate hardness would be 200 milligram per liter CaCO3. We can also, if you can make a chart, if you can visualize a chart, you can also get it that way. And the non-carbonate hardness would be whatever rest is left, 367 milligrams per liter as CaCO3. So that is the answer for this problem. Thank you.